Hello everyone. This video is going to demonstrate how we add resistors in parallel. In a previous video we covered how to add resistors in series, so I recommend you watch that one before starting this one. In that video, I started off by showing the circuit diagram, which consists of multiple resistors that are combined in a bunch of different ways. With the two resistors shown here, you can see that the current coming out of the battery goes through two resistors, one right after the other. The same current that goes through the first resistor then goes through the second resistor. That's a series connection. But after that, you can see that the current comes to a point where it can actually split up and take multiple different paths through the circuit. After going through the paths, the different currents meet up again and recombine on the right side. These resistors are connected in what's called parallel. Remember, the overall goal we're working towards here is to be able to find an equivalent circuit where we replace multiple resistors in the circuit with just one equivalent resistor. The previous video showed how we added resistors that were connected in series, but it turns out parallel is slightly more complicated. To delve into the mathematics of how we add these together, let's discuss a little bit about what is actually happening in a parallel connection. So as you can see, I have three resistors in parallel, and you can imagine that they are hooked up to some battery somewhere. I'm just not going to show all of that here, but we know that when you have resistors hooked up to a battery circuit, there is an electrical current that'll flow into this combination of resistors. I have this current labeled with a capital I, and it comes in and reaches an intersection where there are multiple paths the current can take. In this example, there are three paths. Some of the current, called I1, is going to go up and through R1. Some of the current, I'm calling it I2, is going to go through R2. And some of the current, called I3, will go through R3. How much current goes through each resistor depends on the resistors themselves. There will be another video that will guide us on how to figure out the amount of current in each parallel branch. However, I think you can probably see here that if the original current I splits into I1, I2, and I3, that the total current I is the sum of I1 plus I2 plus I3. So the current gets shared between the resistors, but the overall total amount of current is the same. Then I1, I2, and I3 will end up recombining at the next intersection, and the original current I comes out of the parallel combination. We can use this relationship between the currents to help us calculate an equivalent resistance. In the equivalent circuit, we have a current called IEQ going through REQ, and IEQ is the same total current I as in the original circuit. Now we know that when a current flows through a resistor, there is also a potential drop or voltage drop across that resistor. I'm going to call that delta V. So for R1, we have a voltage drop across it of delta V1. A drop of delta V2 happens across R2, and a drop of delta V3 happens across R3. On the equivalent circuit, we will label the potential drop across the equivalent resistance to be delta VEQ. But what is the relationship with these delta V's? We know that current sort of splits up among the resistors, but what happens with these potential drops? Well, in the series video, I described an analogy where I thought of resistors as hills, where a current that is going up a hill gains energy from the battery, so the battery acts as if you're going up a hill, and then the current gives up that energy by going down the hill. And going downhill is what I'm comparing to resistors. It's not a perfect analogy, and if you're not sure what I'm talking about, go back and watch the video on series resistors where I explain a little bit more about it. Knowing this analogy is not crucial, but I'm including it as I personally think it's a nice way to visualize a circuit. If we think of this current of electrical charges going down hills, meaning going through resistors, you'll notice that the current can take the different paths. We have current I coming in, and we'll consider that I1 goes downhill 1, I2 goes downhill 2, and I3 goes downhill 3. At the bottom of the hills, they meet up again to become the original total current, I. Now the thing with the parallel connection here is that it's three different paths here. So we consider that these three hills start at the same initial height, and at the end, so they can recombine, they have to be at the same final height. So what that ends up meaning is that all the drops are the same. So it sort of reminds me of a little bit of when you go skiing. Everybody takes a chairlift to the top of the mountain to start up, but then you can take multiple ski runs to the bottom based on skill level. All those runs, they end up at the bottom of the chairlift again. Basically, the ski runs are in parallel. So in terms of the voltage drop, the drop across R1 is delta V1, which is going to be equal to the drop across R2, which is delta V2, and is also equal to the drop across R3, delta V3. Now for the equivalent circuit, it means that the drop, delta VEQ, has to be the same as the drops across the original resistors in the original circuit. Overall, the relationship between voltage drops in the parallel circuit can be written mathematically as delta V1 equals delta V2 equals delta V3 equals delta VEQ. In other words, the voltage drop is the same across every parallel branch, while the current is split up and shared among the resistors. With these two relationships established, we can now figure out how to add these resistors. I've cleaned up my diagram here so that I have my two equations. One of the equations is relating to the currents, and the other one is relating to the voltage drops. So now let's apply some math to this. I'm going to bring in our Ohm's law relationship, which provides the relationship between the voltage drop across a resistor, the current through the resistor, and the resistance of the resistor. Now, in this case, I'm going to write Ohm's law in the form of I is equal to delta V over R. You've seen this before. I can also apply this relationship to the equivalent circuit. We know that IEQ will be equal to delta VEQ over REQ. I'm going to start with the equation adding the currents together. I can now write it by subbing delta V1 over R1 in for current I1. So I'm using the Ohm's law relationship in the current equation. I'm going to do the same for I2, I3, and IEQ. So overall I get the relationship delta V over R1 plus delta V2 over R2 plus delta V3 over R3 equals delta VEQ over REQ. But we know from our hill analogy that all the delta V's are exactly the same. So just for simplicity's sake, let's just refer to them all by one symbol called delta V. And notice that because delta V then is in every part of the equation, I can cancel it out from both sides. What I'm left over with is that I get 1 over R1 plus 1 over R2 plus 1 over R3 is equal to 1 over REQ. So we're adding the inverses. Now, to write it a little bit differently, we can get the relationship, and I'm just moving around with some algebra here, where you basically add the inverses, 1 over R1 plus 1 over R2, etc. And then to find REQ, you have to take all of that and take the inverse of it, or raise it to the power of -1. I will take the time to emphasize that a lot of people forget to do this step. They just forget to take that last bit to the power of -1. That is one of the most common things I see on exams, so please be mindful of that. So now we have an equation where we can add parallel resistors together. Now I just want to take a minute and talk about this formula because it leads to some very non-intuitive results. Let me demonstrate that with a bit of an example here. Okay, so notice on the left side here, I have a 2 ohm resistor that's connected to some other part of the circuit here. Just imagine, if you like, that it's connected to some battery, and I'd like to find the equivalent resistance of the circuit. Which, in this case, because it's only one resistor, the equivalent resistance is just equal to that resistor. It's equal to 2 ohms. So you may think, okay, that's pretty obvious. What's so great about that? Well, let's add another 2 ohm resistor in parallel. So in this diagram, I have 2 2 ohm resistors connected in parallel. So if I was going to find the equivalent resistance of these two, I would just do the calculation where you do 1 over 2 ohms plus 1 over 2 ohms, and then you take all of that to the power of -1. That's going to give me an answer of 1 ohm. So why I said this is kind of non-intuitive is because we've now combined two 2 ohm resistors together in parallel and somehow ended up with less overall resistance in the circuit. And that is weird because you would think that if you're adding more resistors in a circuit, you shouldn't get a smaller overall electrical resistance, but we do. So this is what happens, and it does have some interesting effects on circuit designs, which we'll probably discuss in another video when we're doing full circuit analysis. But just to emphasize, I just continue this example where I'm going to have 3 resistors in parallel. Notice when I combine those, the equivalent resistance, REQ, is going to be 0.66666 ohms, or basically 2/3 of an ohm. By adding this third resistor in, we got even less overall resistance. I decided to do 4 resistors to finish it off, and the math now gives us that REQ is now 0.5 ohms. So it seems that the more resistors you add in parallel, the smaller the equivalent resistance in the circuit gets. This should be seeming very weird because it means you're adding more resistors, but you're getting less overall electrical resistance. But this is what happens. This is in contrast, of course, to adding resistors in series, where adding more resistors results in a higher REQ. Okay, let's try an actual example. Here you see that I have 3 resistors connected in parallel. R1 is 2 ohms, R2 is 3 ohms, and R3 is 5 ohms. Let's calculate the equivalent resistance of these 3 resistors. In order to do that, we're going to use our formula for combining parallel resistors. So we have 1 over R1 plus 1 over R2 plus 1 over R3. We'll then take that sum and raise it to the power of -1. In other words, taking the inverse. I'm just going to plug in the numbers now. Now, generally, you're going to plug them into your calculator and get a decimal number, and that's okay. But if you wanted to, you can also use fractions. So when I do 1 over 2 plus 1 over 3 plus 1 over 5, I get 1.03333 and onwards. I just put the little bar over the final 3 to show that 3 is just repeated infinitely. If I take that number to the power of -1, I'm going to get the answer, and I'm going to round it to 0.968 ohms. By the way, if you did it in fractions, that's okay. In fact, it's probably a little better for future calculations if you do it in fractions. And in case you did it in fractions to try out this problem, in fraction form, that 0.968 ohms comes to 30 over 31. So it's also, you could write it as 30 divided by 31 ohms. Now, one thing to note about our answer is that we can check it by noticing that our REQ is smaller than any of the original resistors we started with. As I said before, adding resistors in parallel ends up decreasing the overall resistance. So we have an equivalent resistance of 0.968 ohms, and since we expect our answer to be lower than the lowest of any of the resistors we're adding in parallel, it's 2 ohms here, it looks like we're on the right track. Alright, this is the end of the video. I'd like to thank you for watching and hope you have a great day.